In this lesson, we'll be discussing Dunn's Q-test, which is a post-hoc test for non-parametric data. This test is used to distinguish which groups are significantly different from a pairwise comparison. The question reads, given the data provided from a previous lesson, and a link is provided on your screen, and the rank obtained via the Kruskal-Wallis technique, shown over here, we concluded that at least two treatment group means differed at 0.05 significance level. So in that previous lesson, I showed you how to find these means. I'm not going to go through it in this lesson. You can always refer back to that one. And what we're expected to do now is to use the Dunn's Q multiple comparison approach to calculate the value of Q for all the pairwise differences between the treatments. So we've already rejected the null hypothesis in favor of the alternative hypothesis, but now we want to know which of these treatments are in fact different from one another. Now before we do any of that, Dunn's test can be used for both equal and unequal sample sizes. If you look at the formula carefully, you'll notice that there is a capital N and a little n. Capital N represents the total number of observations, whereas little n represents the observations per treatment. In addition, it is the equivalent post-hoc test to the Bonferroni method, and we've done that in a previous lesson. So feel free to compare that afterwards. So as we did with the Bonferroni method, we have to compare each of these treatments one by one. For example, treatment 1 and treatment 2 need to be compared. Treatment 1 and treatment 3, treatment 1 and treatment 4. Furthermore, we have to look at T2 and T3, T2 and T4, and finally T3 and T4. So we have to calculate 6 different values of Q and compare them to this value. Remember in the question they wanted at 95% confidence, so we'll look at this column, which has an alpha value of 0.05. There are 4 treatments we're dealing with, so K is 4, and this is the value that we will be comparing each of those Q values we end up with. With that being said, let's begin by comparing T1, treatment 1, and treatment 2. We'll start with the hypothesis. The null hypothesis will be that the mean rank of treatment 1 equals the mean rank of treatment 2, which essentially means that they are not any different. The alternative, on the other hand, suggests that they are different. So I've represented that with not equals to. Remember, our critical value is 2.639. If our value of Q is less than that, then we do not reject the null hypothesis, which means the treatments are not any different. Let's calculate Q. Q for treatment 1 and 2 is equal to, let's look at the rank means, 8.1 and 13.9. 8.1 minus 13.9, and they are surrounded with these absolutes, which means that if our difference is negative, it becomes positive. Over, and our square root contains n, capital N is the total number of observations, which is 20. 20 bracket 20 plus 1 is 21 over 12. And in parentheses, we have 1 over 5, 5 observations per treatment, plus 1 over 5. I'll show you how to do this on your calculator. First, we'll do the numerator, 8.1 minus 13.9. That's a negative value, so I'll multiply that by negative 1 just so that I make it positive, giving us 5.8. Divided by, now the denominator. In parentheses, 20 times 21 divided by 12, that's this factor. And again in parentheses, 1 over 5 plus 1 over 5. And we end up with a Q value that is 1.55, 1.55. 1.55 is less than the critical value of 2.639, which means that we cannot reject the null hypothesis. Do not reject null hypothesis. We can't do that in favor of the alternative. So treatment 1 and treatment 2 are no different. All right, rather than wasting your time, since this is a tutorial You have to do this again for treatments 1 and 3, 1 and 4, 2 and 3, 2 and 4, and then lastly 3 and 4. Here are the values that you should get for each one. Okay, notice that these Q values are all less than 2.639, leaving us with the last one comparing 3 and 4. The Q value for treatments 3 and 4 is equal to 2.7258. And that value is greater than the critical. Therefore, we would reject the null hypothesis. And the null hypothesis here would have been the mean of the ranks of treatment 3 is equal to the mean of the ranks of treatment 4. And the alternative will be that they're not equal. And that's a good thing. Because this Q value is greater than the critical value, we would have to reject this one in favor of the alternative hypothesis, suggesting that the mean of the ranks are different. Therefore, out of all of these treatments, treatment 3 and treatment 4 were significantly different, and there was no significant difference for the 5 other comparisons. If you look back at the Bonferroni video that I've published a while ago, the same conclusion you would find if you use that method as well. And so there you have it. If you have any questions, leave them in the comment section below. And as always, thank you for watching.